Okay, in this video we're going to go over homework problem number 17 in section 2.5. So this is a surface area problem that we did in class. So let's read it first because we have to figure out two things. For optimizations, you need to determine your constraint. So I'm going to write constraint here. Your constraint and also your objective function. So that's our first job when we read. So let's read. Okay, so I know our focus will be on a surface area. It says find the dimensions of the closed rectangular box. Closed means that it has a lid. So it's not an open box. And this triangular box has to have a square base and a volume of 8,000 cubic centimeters that can be constructed with the least amount of material. So you have one sentence with a great deal of information. So just speaking in generalities initially, your constraint is that your volume, let me get my pencil going, your volume has to be 8,000 centimeters cubed. So that's your general constraint. Your objective function, the objective is to minimize the surface area of your box. Okay, so that's the big picture. So let's look at the specifics. So we're going to go on the next page and we're going to put in my homework. Okay, so this is my homework sheet. So you can see that I have some things already written on here. So I'm going to just highlight the key points. Okay, first thing, you want to draw your picture. So here's my picture here of the rectangular box, and I know that my base is x by x, and my height or my width of the box is y. So you want to have that picture. So your objective function is to find the surface area that's going to be minimal and still have the constraint of the volume equals 8,000 centimeters cubed. So we talked about volume in generics on the previous page. So let's look now right here. Here is my constraint. My volume is area of the base times the height. So x squared times y has to equal 8,000 centimeters cubed. Okay, next, let's spell out the objective function. It's right here. Surface area is going to equal the area of this front right here, so that's x times x, plus the area of this back. So I have 2x times x, so that is 2x squared, and that's right there. Then the rest of the surface area, this surface right here in blue is x by x. So is this surface on top where the lid would be. So is this side panel down here. And so is the very bottom. So we have 4 sides that are x by y. That is the surface area, and you have to be able to come up with this. All right, our next step is to look back at the constraint. The constraint is going to be used to isolate your variable y. So right over here, we're going to write y in terms of x squared in this situation. So y equals 8,000 divided by x squared. Because we have to take the derivative of the surface area, we need to make sure that we have it in terms of only one variable. So our y variable right over here is being replaced by this y variable from the constraint. So that gives us this equation. Simplify it, write it in a form where you can take the derivative and then take the first derivative. So here's our first derivative. Set that derivative equal to 0 and solve for your one variable, which is x. So that takes us all the way down to this point. X is 200. I then can take my x and plug it back in my constraint, and I'll get a y of 20. So my dimensions, which are right here, are 20 centimeters by 20 centimeters by 20 centimeters. Now, I am not done until I prove that what I have found is indeed the minimum surface area. All I know is that this surface area has a first derivative that equals 0 when x equals 20. I don't know that that's a max or a min unless I do either the first derivative test or the second derivative test. We're going to do the second derivative test. So take your second derivative of your surface area, and you're going to get 4. Do this correctly by bringing up x squared as x to the negative 1, and you'll get plus 64,000 over x cubed. Now, whatever I plug in x is going to make this entire expression greater than 0. If it's greater than 0, then that means that my surface area equation must be concave up. If it's concave up, it's going to look like this, and therefore the point where the slope was 0 guarantees that I will have a minimum because my function was concave up. So that's the essence of this problem. Surface area, it should not be something that intimidates you, and you want to be able to follow through on all the parts of this. I said in class that most mistakes I see are either in assigning the variables correctly in the objective function and the volume, or in doing basic algebra. So don't rush through the initial steps. Taking the derivative should be the easiest part of the problem. Assigning the constraint and the objective function and making the objective function written in terms of only one variable and getting your sketch, all those steps should take you a little bit more time than does taking the derivative. Remember to always take the second derivative or do the first derivative test to prove that you have indeed gotten the value that you were looking to get. So that's the end of 17. Go back over this and make sure that you understand it.